Hey everyone, thank you very much. The Swinburne train continues. So I'm here to talk about outflows in edge-on galaxies. Is that advancing? No good? There we go. So hopefully by this point you're convinced of the importance of outflows in general, so I don't have to go over that. That's good. What I want to talk about is the shape and size of outflows. So here's my picture of M82. You've seen it a few times so far. It's, as you'll know, a nearby edge-on starburst with probably the most well-studied outflow. And we have this problem in that our models of galaxy evolution are really dependent on a very small number of galaxies like M82 or NGC 253. And this is potentially a problem since the outflow in this galaxy is really particular. You know, we're being driven by this very strong central starburst that's giving rise to this very characteristic bicone shape. So what our models of galaxy evolution are perhaps missing is what happens to your outflow when your galaxy properties change, like mass and star formation rate and metallicity, and just how your starburst is distributed throughout the disk. And so you've heard a bit about the Duvet survey already. With the methods and tools that we've developed as part of that study, we can do various things depending on the orientation of the galaxy. You heard from Bron talking about the face-on work just now. In our edge-on galaxies, we use a surface brightness-based method that we've developed in order to define an outflow region. And with that region defined, we can then measure really basic outflow properties like extent and width and opening angle. Cool. And so the pilot target for our edge-on work has been McPherson 1486. It's a nearby edge-on starburst at really low metallicity. We can see in this HST imaging, we've got the galaxy disk at the center there, and there's this extended filamentary structure that looks quite a lot, that's consistent with the minor axis outflow. And so we're using this galaxy as a test case to develop our methods for defining outflow regions in these galaxies. So we can have a quick look at some results on this galaxy. So I'm showing here the surface brightness profile in O3 and H beta in these minor axis regions. This is a really good place to start since it's a pretty simple measurement that doesn't require too many assumptions, and it's pretty empirically motivated. And we've overlaid the H alpha surface brightness profile in M82 for comparison. And we can see that in this galaxy, we recover this really extended minor axis emission profile out to just under 10 kiloparsecs. That's right to the edge of our field. That's similar to what we see in M82. Now, since this galaxy is really, really edge-on, we don't get any information about outflow velocity. But under standard assumptions, this more extended surface brightness profile corresponds to higher gas velocities. And so with our resolved observations of emission across this galaxy, we've developed a method that uses the surface brightness in order to define an outflow region. So I'm showing here the velocity dispersion on the left and a map of the emission line flux on the right in the O35007 emission line. And we've got overlaid in red the outflow region that our process defines. So we define a disk region to begin with, and we treat each outflow lobe separately. And then we find the brightest pixel in each row parallel to the galaxy disk. And we treat the median position of those pixels as the outflow center. And then we can find the 50 and 90% widths in terms of surface brightness. And this is a really effective and automated technique. Obviously, if you have like an IFU cube of a galaxy, you can look at the kinematics in your disk and your gas, and you can make determinations about the outflow region in that way. But often it's just more feasible to get like a narrowband emission map over a starburst. And what we're trying to show here is that if you can get that, you can start to measure some basic outflow properties. And so if we take this to be the outflow region, you get a very wide outflow that implies covering fractions of order 100%, a very extended outflow that breaks from the disk at roughly a kiloparsec and then extends to a 90% distance upwards of 6 kiloparsecs. We can also directly measure the opening angle just by fitting a line to the outflow profile that we detect. And here at the 50% width, we measure an opening angle of 20 degrees, which I can give some context to in a moment. Since we do have IFU observations here, we can look at the kinematics in the gas and see how that corresponds to what we define as an outflow region from the surface brightness. And so we can look at the velocity dispersion on the left, and we can see the low dispersion disk at the center, those very dark points. And then these very bright white points, these regions of very high dispersion, agree really well with the outflow region that we define from the surface brightness alone. So what we're saying here is if you can get this narrowband emission map, you can measure opening angles and widths and extents in a really systematized way. And so with the outflow region defined, we can look at the mass outflow rate in these outflow regions. So in the upper outflow region, we get 1.2 solar masses per year. In the bottom, 1.3 for a mass loading factor of 0.7. That's a lot of numbers, but we do need to exercise a bit of caution with the absolute value of these mass outflow rates, since there's a lot of assumptions that have to go into these numbers, especially in edge-on galaxies and especially in this galaxy. I can go into some of those in a moment if anyone's interested. But what these numbers are useful for is for looking at the relative contribution of the different components of the outflow in this galaxy. So we can see the minor axis outflows are pretty comparable here. And then we can also use some of the down-the-barrel work that Bron was talking about in order to look at the edge of the disk. We can fit Gaussian models to the observed emission lines across the disk, and in the pixels where we detect this secondary blue-shifted outflow component, we can calculate mass outflow rates and outflow velocities. And what we find is that there's a significant amount of flux in outflows along the disk edge. The velocities that we're seeing here are like well below the escape velocity for the galaxy, so we expect that this gas is just going to be reaccreted. But it's a not insignificant contribution to the total mass outflow rate budget for the galaxy. And this is telling us something about the shape of the outflow in this galaxy, where we're not seeing just like an isotropic spherical outflow or this clearly biconical outflow, but we're seeing this very complex shape. And this disk edge outflow is contributing about 25% in terms of mass. And that means that the total mass outflow rate that you would calculate if you observe this galaxy in different ways and in different orientations is going to perhaps differ quite wildly from what the actual value is. And this disk edge outflow perhaps is something to consider if you are a simulator. But with the methods that we have developed, obviously our goal is to apply them to a larger sample of galaxies. And so there's 4 more edge-on targets in the Duvet survey. This is one of them. It's KISSA 1578. It's slightly more massive than McPherson 1486. It's also a bit less edge-on, so there's some projection effects that I need to disentangle here. But our preliminary results, at least, are showing opening angles and mass outflow rates that are quite similar to what we see in McPherson 1486. And here's another galaxy on the lower mass end this time. There's an object in the frame on the bottom side, so the bottom outflow we have to ignore, but in the top outflow at least, again, we're seeing opening angles and mass outflow rates that are really, really similar to what we see in McPherson 1486. And here's a handful of galaxies from throughout the literature for which I was able to find opening angle measurements, and this is across like 4 or 5 orders of magnitude in terms of stellar mass, and we're seeing these really consistent values of opening angle of like 20 to 30-ish degrees. So as we're increasing the sample of galaxies for which we have these kind of measurements, we're making these determinations about what is a typical value for these kind of quantities. But it's clearly not a universal quantity. You saw NGC 1569 in Magdalena's talk just now, and this outflow is very different. We've got gas blowing out all over the place. So still trying to understand what's typical and what isn't. And we can look at the similarity in these edge-on results to results that you've already seen today. This is, I think, an old version of a plot that Bron showed, where she was finding outflows right across the face of the disk, but with most of the mass contained within a much smaller, more centralized region. And that's exactly what we see in edge-on results on McPherson 1486, where we have these very wide outflows at the 90% width that are implying like covering fractions of order 100%, but then the majority of the mass is contained within a much more central region. And these agreements in opening angle and the distribution of mass throughout the outflow are telling us something about how the starbursts driving these outflows are distributed throughout the disk, where it seems to be that we're seeing in all these galaxies these very, very central starbursts that are driving these outflows. And it's possible galaxies are all have a similar thing like that. So just to finish up and summarize, with the methods that we've developed as part of Duvet, in our edge-on targets, we're able to define outflow regions based on surface brightness alone. And with our outflow regions defined, we can measure these basic properties like width and extent and opening angle. And since our technique is very quick and very systematic to apply. We're hoping to greatly increase the number of galaxies for which we have these observations. And then in concert with our down-the-barrel results, we can make determinations about the three-dimensional shape of outflows. Thank you very much.